సబ్స్క్రైబ్ చేయండి. ఫర్ మోర్ అప్డేట్స్ బెల్ ఐకాన్ క్లిక్ చేయండి.
Now we are going to discuss TDS equations. There are three TDS equations due to thermodynamics, Maxwell thermodynamic relations. So first TDS equation and second TDS equation and third TDS equation. One by one we'll discuss. First TDS equation. First TDS equation. So first of all, the entropy defined as the function of entropy is denoted as S, the function of temperature and volume. In the first TDS equation, the entropy is defined as the function of temperature and volume. So in this case, ds is the perfect differential, then partial differentiating this equation. Then we can write ds is the perfect differential. So then the partial differentiation of this equation, dou s upon dou t at v into dt plus dou s upon dou v at t into dv. So here dou s upon dou t at v into dt, dou s upon dou v at t into dv. This equation. So multiplying this equation both sides with t. So then this equation can be written as Tds equals to t into dou s upon dou t at v into dt plus dou s upon dou v at t into dv. Sorry, this multiply the t. But TDS is already, we know that is the TDS is the thermodynamics second law, that is the dq equals to TDS. Then this equation can be written as dou q upon dou t is equals to here t dou s upon dou t at v. dq equals to TDS. Then this equation can be written as dou q upon dou t equals to t into dou s upon dou t at v. So t into temperature into change in entropy is called, this is the temperature, change in entropy is called specific heat at volume. So this equation can be written as, TDS equals to t into dou s upon dou t into v is the Cv. So in this place we substitute this equation, Cv into dt plus t into dou s upon dou v at t into dv. Okay, next thermodynamic relation, Maxwell's thermodynamic relation, potentials. Maxwell's second thermodynamic relation is dou p upon dou t at v is equals to dou s upon dou v at t. So in the place of dou s upon dou v at t, we substitute this equation. So then this equation can be written as Tds equals to Cv dt into dou p upon dou t at v dv. So here t. So Tds equals to Cv into dt plus t into dou p upon dou t at v dv. This is the first Tds equation. First Tds equation. In second Tds equation, the entropy can be defined as the function of second equation, second Tds, the function of temperature and pressure. Temperature and pressure. Similar as first Tds equation, ds is the perfect differential. Then this equation partial differentiating. So dou s upon dou t at p, dou s upon dou t at p into dt plus dou s upon dou p at t into dp. So multiplying this equation on both sides with t, then this equation can be written as T ds t into dou s upon dou t at p dt plus t into dou s upon dou p at t into dp. Already we know that Tds is equals to thermodynamics second law, that is the dq equals to Tds. dq equals to Tds. Then this equation can be written as dou q upon dou t is equals to t into dou s upon dou t at p. So this equation can be written as T into temperature into change in entropy, that is called specific heat at pressure. So in this place we substitute this equation. What is this place? T into dou s upon dou t at p is equals to Cp. So Tds. So then Tds equals to T into dou s upon dou t into p is the Cp into dt plus T into dou s upon dou p at t into dp. Now we write the thermodynamics, Maxwell's thermodynamics fourth relation. Maxwell's fourth thermodynamic relation, that is the dou v upon dou t at p is equals to minus dou s upon dou p at t. So in the place of dou s upon dou p at t, we substitute this equation, but in minus. So this equation can be written as Tds is equals to Cp into dt minus, because this is the minus dou s upon dou p at t minus dou v upon dou t at p into dp. Already t. This is the second thermodynamic relation. This is the second TdS equation. Second TdS equation. In third TdS equation, the entropy is defined as the function of pressure and volume. So similar as first and second, if ds is perfect differential, then this equation partial differentiating. So dou s upon dou p at v into dp plus dou s upon dou v at p into dv. Same as multiplying on both sides with t, then tds equals to t into dou s upon dou p at v into dp plus t into dou s upon dou v at p into dv. This equation can be written as tds is equals to t, here dou s upon dou t into dou t upon dou p. Here dou t is the cancel, dou s upon dou p remaining is v into dp. Same as t dou s upon dou t into dou t upon dou v at p into dv. So this equation can be written as, further simplification, t ds is equals to t dou s upon dou t at v, dou s upon dou t at v into dou t upon dou t at v, dou t upon dou p at v into dp plus t into dou s upon dou t at p into dou t upon dou v at p into dv. So in the first TdS equation and second TdS equation, this equation in this place, this is the specific heat at volume, this is the specific heat at pressure. So the temperature into change in entropy is the specific heat, the temperature into change into entropy, this is the specific heat at volume at pressure, So this equation can be written as TdS is equals to Cv into dou t upon dou p at v into dp plus, in the place we substitute Cp dou t upon dou v at p dv. This is the third TdS equation.